OK, so in this set of videos, we are going to cover an exploit that I like to call the off-by-one exploit. I don't know if that's the official term, but it's something you'll see in the projects. And it really tests your understanding of how the call stack works. So if you haven't already, I would definitely recommend going back to the second lecture and really making sure you have a good grasp on how the EBP, the ESP, and the EIP change around when a function gets called and when the function returns, because that's really critical to understanding this particular exploit. So what exploit am I talking about? So let's consider some code like the one down here. We have a main function, and it calls a vulnerable function. And then the vulnerable function defines a name array of size 20. And then it calls fread, which writes from the user input into the name character array. And specifically, it looks like whoever wrote this code made a typo. And instead of writing that you can write 20 characters into the name array, they said you can write 21 characters. So that's kind of an issue. And in particular, what issue does this cause? How do we exploit this? So whenever I see a kind of unfamiliar exploit like this one, where I'm not really sure what's happening, something that I find useful is I like to first draw the stack diagram. So if you don't have one of these pictures, it might be kind of hopeless to try and exploit this. So I find these really helpful. So this diagram says, well, when I first call main, it has an RIP and an SFP. Those are my saved register values, like always. And then there's no local variables in main, so I don't have to put anything here. When I call vulnerable, it takes no arguments, so don't have to put anything there either. And now I call vulnerable. And when I call vulnerable, there were no arguments, so I go straight to pushing the RIP on the stack, the SFP on the stack. And then the user defines name. And when they define name, that's a local variable. It's 20 bytes, so it takes up 5 rows. Each row is 4 bytes. So that's my stack diagram. And I've also noted in this particular case that the EBP points at the top of the vulnerable stack frame, which is right here, and the ESP points at the bottom of the vulnerable stack frame, which is down here. One tiny little note that sometimes people bring up, but it is not the most important thing here. If you take an operating systems class like CS162, you might realize, OK, actually, when the operating system calls main, it doesn't really have an RIP and an SFP. It does some other fancy things so that you can return back to the operating system. For this class, we're not an operating systems class, so I don't really care. So we'll just abstract it away and say that main has an RIP and SFP like everyone else. But if you really care, you can go take an operating systems class and learn the real truths behind how main is called. But for our purposes, we'll just say RIP main, SFP main. It's good enough for this exploit. So that's the stack diagram. It's always the first thing that I do. I draw the stack diagram. Then the next thing I do, now that I have my stack diagram, is I can start asking myself, well, what parts of memory can I overwrite? So as an attacker, the only thing I can do is I can provide some input, and the input gets written onto the stack. So something useful whenever I see these unfamiliar exploits is I ask myself, what parts of memory can I overwrite, and what parts of memory can I not overwrite? And that gives me some idea of the things I should be looking out for. I can overwrite this part of memory, so I should really think about what dangerous things I can do here. Or I can't overwrite this part of memory, so I don't even have to think about this exploit. It's not going to work because I can't touch this part of memory. So in this case, it looks like, well, I can write 21 bytes of data into a 20-byte character array. So if I start writing at name, and I write 4, 8, 12, 16, 20, I can write one extra byte, the 21st one, and that's it. So what I've shown here is this stuff in yellow that I've highlighted, that's the only stuff I can overwrite. I can overwrite all the bytes of name to whatever I want. And I can overwrite this one byte of the SFP. Not all 4 of them, just one. And also, kind of crucially, I can't overwrite the RIP. So I can't play my usual trick where I take RIP and I change it to point at shellcode. That's no longer going to work because I can't overwrite the RIP. So just by writing down what I can and cannot exploit, I've already ruled out my favorite classic buffer overflow where I just overwrite the RIP pointed at shellcode. It's not going to work in this case because I cannot overwrite that part of memory. So just by setting up the question like this, drawing a very good, careful stack diagram, and highlighting the things that I can and cannot exploit, this already gives me a pretty good idea of where I should be looking for exploits. In particular, probably right there. So that's the setup of this question. And coming up next, we'll see how you can actually exploit this code, even though you can overwrite one single byte only.